According to the National Electrical Code, specifically Article 430.32a, each motor must be protected against overheating due to overload. Also, according to Article 430.32c2, where two or more motors are connected to a single overload device, the rating of the overload device cannot exceed the sum of the full load current ratings of the motors. Therefore, if you are replacing a single motor driving two fans with two separate motors, you are correct in needing to protect each motor with its own overload unit. Using a single overload unit for both motors would present a problem because the overload unit would trip if either motor experiences an overload, leaving the other motor unprotected. Firstly, ensure that the overload units are correctly sized for the specific motors you are using. The overload unit should be selected based on the motor's full load amps, service factor, and ambient temperature. Secondly, the overload unit should be installed in a location where it is easily accessible for maintenance, inspection, and resetting. Overload protection is a critical aspect of motor control and safety. Its main function is to protect the motor from damage due to excessive current. This excessive current can be caused by various factors, including mechanical overload, locked rotor conditions, or phase loss. The overload unit monitors the motor's current and trips the circuit if the current exceeds a preset value for a certain period. The National Electrical Code outlines specific requirements for overload protection to ensure the safe and reliable operation of motors. The code mandates that each motor must have overload protection sized appropriately for its full load amps. The overload protection can be provided by various devices, such as thermal overloads, magnetic overloads, or electronic overloads. Thermal overload relays are the most common type of overload protection. They operate on the principle of heat generated by the motor's current. The overload relay consists of a heater element connected in series with the motor and a bimetallic strip or melting alloy. When the motor current exceeds the overload setting, the heater element heats up, causing the bimetallic strip to bend or the melting alloy to melt. This action trips the overload relay, disconnecting the motor from the power supply. Magnetic overload relays use an electromagnet to sense the motor current. When the current exceeds the overload setting, the electromagnet pulls in an armature, which trips the overload relay. Electronic overload relays offer more advanced features and greater accuracy than thermal or magnetic overloads. They use electronic circuits to monitor the motor current and can provide various protective functions such as phase loss protection, undercurrent protection, and ground fault protection. Selecting the correct overload unit is essential for effective motor protection. The overload unit must be sized appropriately for the motor's full load amps, service factor, and ambient temperature. The full load amps of the motor is the current the motor draws when operating at its rated horsepower and voltage. This information can be found on the motor's nameplate. The service factor of the motor is a multiplier that indicates the motor's ability to handle occasional overloads. Motors with a service factor of 1.0 can operate continuously at their rated horsepower, while motors with a service factor greater than 1.0 can handle occasional overloads without overheating. The ambient temperature is the temperature of the air surrounding the motor. Overload relays are temperature sensitive, and their tripping characteristics can be affected by ambient temperature. When selecting an overload unit, it is essential to consider the motor's service factor and the ambient temperature to ensure that the overload unit will trip at the correct current level. Installing the overload unit in an easily accessible location is crucial for maintenance and resetting. Overload relays can trip due to various reasons, such as temporary overloads, voltage fluctuations, or equipment malfunctions. When an overload relay trips, it is essential to identify and correct the cause of the overload before resetting the relay. The overload unit should be installed in a location where it can be easily inspected and reset. The location should also be free from obstructions and readily accessible for maintenance personnel. Furthermore, it is important to regularly inspect and test overload relays to ensure they are functioning properly. Overload relays can fail over time due to wear and tear, corrosion, or damage from electrical surges. Regular inspection and testing can help identify potential problems before they lead to motor failure. Testing overload relays typically involves using a test kit to simulate an overload condition and verify that the relay trips at the correct current level. The test kit should be calibrated regularly to ensure accurate results. In addition to overload protection, motors also require short-circuit protection. Short-circuit protection is designed to protect the motor and the electrical system from damage due to short circuits. Short circuits can occur when there is a fault in the motor winding or in the wiring connected to the motor. Short-circuit protection is typically provided by fuses or circuit breakers. Fuses are overcurrent protection devices that contain a fusible link that melts and opens the circuit when the current exceeds a certain level. Circuit breakers are overcurrent protection devices that use a mechanical mechanism to trip the circuit when the current exceeds a certain level. Selecting the correct fuse or circuit breaker for short-circuit protection is essential for ensuring the safety of the electrical system. The fuse or circuit breaker must be sized appropriately for the motor's full load amps and the interrupting capacity of the electrical system. The interrupting capacity is the maximum fault current that the fuse or circuit breaker can safely interrupt. The National Electrical Code provides specific requirements for short-circuit protection of motors. The code mandates that the short-circuit protection device must have an interrupting capacity sufficient to handle the available fault current at the motor terminals. In addition to overload and short-circuit protection, motors may also require other types of protection, such as phase loss protection, undervoltage protection, and ground fault protection. Phase loss protection is designed to protect the motor from damage due to loss of one or more phases of the power supply. Phase loss can occur due to blown fuses, open circuit breakers, or damaged wiring. Undervoltage protection is designed to protect the motor from damage due to low voltage conditions. Low voltage can occur due to voltage sags, brownouts, or equipment malfunctions. Ground fault protection is designed to protect personnel from electrical shock due to ground faults. Ground faults can occur when there is a fault in the motor winding or in the wiring connected to the motor that allows current to flow to ground. The National Electrical Code provides specific requirements for these additional types of motor protection. The code mandates that these protective devices must be installed and maintained in accordance with the manufacturer's instructions. Proper motor protection is essential for ensuring the safe and reliable operation of motors. Overload protection, short-circuit protection, and other types of protection can help prevent motor damage, electrical fires, and electrical shock. By following the National Electrical Code requirements for motor protection, you can ensure that your motors are properly protected and that your electrical system is safe. Remember to consult with a qualified electrician to ensure that your motor protection system is properly designed and installed. This will help to ensure the safety and reliability of your electrical system. In summary, when replacing a single motor driving two fans with two motors each driving a fan, each motor must have its own overload protection sized appropriately. This is to prevent one motor's overload from disabling both fans and to ensure each motor is individually protected against overheating. Consult the National Electrical Code and a qualified electrician for proper sizing and installation. Proper overload protection is not just about code compliance, but also about ensuring the longevity and safe operation of your equipment. Ignoring these requirements can lead to costly repairs, downtime, and potential safety hazards. Therefore, it is critical to prioritize motor protection and to invest in the appropriate protective devices. By doing so, you can minimize the risk of motor failure and ensure the continued operation of your critical systems. Furthermore, it is important to remember that motor protection is an ongoing process. Overload relays and other protective devices should be regularly inspected and tested to ensure that they are functioning properly. Any signs of damage or wear should be addressed promptly to prevent future problems. Regular maintenance and testing can help to extend the life of your motors and to prevent costly downtime. Finally, it is important to stay up to date on the latest changes to the National Electrical Code and other relevant standards. The code is constantly evolving to reflect new technologies and best practices. By staying informed, you can ensure that your motor protection system is compliant with the latest requirements and that you are providing the best possible protection for your motors. Remember, a well-designed and maintained motor protection system is a critical investment in the safety and reliability of your electrical system. It is an investment that will pay off in the long run by preventing costly repairs, downtime, and potential safety hazards. So take the time to understand the requirements for motor protection and to ensure that your system is properly designed and installed. Your motors, your equipment, and your personnel will thank you for it. Firstly, always consult the motor nameplate for the full load amps. Secondly, refer to the NEC tables for appropriate conductor sizing and overcurrent protection. Thirdly, ensure all connections are torqued to the manufacturer's specifications. In addition, documentation of the installation, including the selection of overload units and their settings, is important for future maintenance and troubleshooting.